Welcome everybody, and thank you, Nick, for the introduction. As you said, my name is Justin Walsh, Application Engineer with Vaisala. Today we'll be discussing the fundamentals of humidity and its measurement, along with some maintenance considerations and best practices. As he also mentioned, we'll be having a question and answer session at the end of the webinar, but I do encourage you to enter your questions into the chat, just so that we can have them recorded, and then I'll do my best to answer them all at the end. And if there's something I don't get to, or if it's a more obscure question, I'll do my best to answer them via email afterwards. So I'll begin the presentation with the basics of humidity and how it behaves and how we can relate to it. Then we'll look at the different ways we can measure and quantify humidity. Next, we'll cover some important aspects of calibration. And lastly, we'll cover some installation best practices and common pitfalls that we've seen in our experience. For those of you unfamiliar with Vaisala, I'll quickly give you some background about us. Vaisala started in weather measurement over 80 years ago, and for over 45 years, we've been bringing that expertise to the wide variety of controlled environments found in industry. Around the world, people depend on our instruments to safeguard valuables, such as the Mona Lisa, and in critical processes like pharmaceutical manufacturing. In addition, our sensor is the one that helped NASA find water on Mars. Our investments in research and development create tools to make observations for a better world. We strive to promote safety, energy efficiency, and decision-making through environmental measurement and related services. So we relate to and interact with humidity in several different ways, whether it be our own comfort, safety, or the quality of the products we produce. And so I like to start with the basics so that we have a solid understanding. The starting point for understanding humidity is to know that we're talking about water vapor, or water in the gaseous phase. This means that the individual water molecules are free of each other and can move freely in the given space. They're not bonded to each other as we know water molecules tend to do. We could also think of humidity as water dissolved in air, although this is not quite accurate. Water vapor can exist in a vacuum and does not require a medium such as air or another gas for it to evaporate into. It's important to note that the properties of water vapor are mostly determined by the water vapor itself and not the other gases that might be involved in the mixture. Now, as water vapor consists of individual water molecules that are far too small for the eye to see, we cannot see humidity in the air, and a common mistake is to confuse steam or mist with humidity. Steam and mist, as well as clouds, consist of small droplets of condensed liquid water. These droplets are so small that they behave almost like a gas. They're suspended in the air and can move around in a random manner. These tiny droplets actually consist of billions of water molecules bound to each other to form one small droplet of liquid water. And in fact, a typical raindrop is about 2 millimeters in diameter, millions of times the volume of an average cloud droplet. Let's look at how we begin to quantify humidity. As said, water vapor is a gas, and the gas molecules are free of each other's influence. Think of small spheres that randomly bounce around without losing any speed when colliding with each other or with surfaces. Now let's look at the box in the lower right-hand corner with the gas molecules inside. The gas molecules bump around with each other and on the walls of the container. In our macro world, these impacts are observed as pressure. The more molecules we have, the more often they bump into the walls of the container, and the higher the pressure is exerted by the gas. Now in the second container in the upper right, we don't have any gas molecules. So that pressure in the container is zero, which would be an absolute vacuum. On the other hand, if we increase the temperature of the gas in the closed container, the thermal energy makes the molecules move faster, and we can think of the spheres bumping into the walls with higher speeds. And we would observe this as an increase in the pressure. So given this, it's fair to assume that we can define the number of molecules in the gaseous form in units of pressure. And in this discussion, I'll be using the SI unit of hectopascals, which is the same as millibars. So if the only substance in our otherwise empty container was water vapor, we could easily determine the amount of water in the container by measuring the pressure exerted by those water molecules. However, in real life, humidity is most often mixed with other gases. Like in the case of dry air, which consists of nitrogen, oxygen, and other gases like carbon dioxide. All these substances behave the same way as the gaseous water molecules. Where water differs is in its unique properties, where it can exist frequently in two different phases, water and gas. It can even exist in three states at the same time, which is at the freezing point, and this is also called the triple point. And so we can have water as gas, liquid, and in solid phases at the same temperature. Because of this, we can treat water vapor measurement a bit differently than the other gases. So how does this mixture of air molecules impact the total pressure? Well, John Dalton conducted experiments with different gases in the early 1800s. He measured the pressures of the individual gas components and then mixed the components together. He found the total pressure was indeed the sum of the pressures of the different components in the mixture. This is known as Dalton's law, and the pressure of a single component is called the partial pressure. In the case of humid air, we don't have to be concerned with each individual component in the mixture. We can simply think of the mixture made of two components, the water vapor, and then everything that makes up the dry air. This illustration depicts this situation. When we have water molecules and water molecules of the air components in similar molar quantities, exerting equal vapor pressures of 500 hectopascals, the total pressure of the gas mixture would be 1,000 hectopascals, or 1 bar. Now that we have a better idea of water vapor and how to quantify the amount of different gases with partial pressures, we can dig a little deeper. So let's look at the phase change from liquid water to gas, or evaporation. When the water molecules are in liquid phase, they are so close to each other that the natural attraction between the water molecules holds them together and slows down their movement. Just like gases, liquids are fluids where the molecules are in constant movement. The molecules don't have the same speed, however, and there is a distribution of speeds. Some molecules with enough speed will come to the surface with enough energy to break free from the other molecules and phase change from liquid to gas, which is called evaporation. Inversely, some molecules lose enough energy to be caught by the molecules in the liquid phase, and this is condensation. Condensation and evaporation happen simultaneously and independently of each other. And here, this video illustrates the two processes. In the beginning, there's no water in the gas phase. With time, the gas molecules start evaporating from the water surface. Simultaneously, the gaseous water molecules start to return into the liquid phase. And while the two processes reach equilibrium, meaning the rate of evaporation equals condensation, this is what happens in the closed system. See, does that still go? Sorry. I think it stopped when I moved. In the equilibrium, and in this example, the air volume becomes saturated with water molecules. And saturation means the volume cannot hold any more water vapor. And the pressure of this natural equilibrium is called the saturation vapor pressure. This condition will hold until some external force interacts with the volume. So is the saturation vapor pressure and the amount of water vapor that can exist in the gaseous phase constant? No. The likelihood of a water molecule to escape from the liquid phase is higher when the molecules have more energy. And this is governed by what we observe as temperature. So having a higher temperature causes the rate of evaporation to increase. Regarding condensation, the water molecules are moving faster and therefore less likely to get caught in the liquid phase. This means the higher the temperature, the slower the rate of condensation. So temperature has an impact on both evaporation and condensation, which means the saturation vapor pressure is subject to temperature. And in fact, this relationship is exponential. So let's look at this video that illustrates our example of liquid water that appears in a closed container. In this video, the temperature increases, and you can see how the equilibrium moves from liquid phase towards the gas phase, increasing the number of gas molecules, increasing the saturation vapor pressure. And as the temperature decreases, you'll see that molecules lose energy and are more likely to condense and get trapped back into the liquid phase. So that brings us to the unit of relative humidity, which is one of the more commonly known humidity variables. By definition, relative humidity is the proportion of water vapor pressure to the saturation vapor pressure at a given temperature. Although using glasses full of liquid water may be a poor example when talking about gases, it's a pretty relatable visual. So now, if the saturation vapor pressure was the glass, which is the maximum amount of water that can be held, the relative humidity is the percentage of the glass which is filled. On the left side, the glass is smaller, meaning the saturation vapor pressure is lower. This would also mean the temperature is lower. The glass is 90% full, meaning the relative humidity is 90%. The glass on the right is also 90% full, meaning 90% relative humidity. But in this case, the glass is bigger, meaning the saturation vapor pressure is higher, which is a result of the higher temperature. In summary, the relative humidity value may be the same, although the total amount of water is very different. This is the reason we're talking about relative humidity, as it is relative to the saturation point at a given temperature. And relative humidity may be one of the most misunderstood quantities for humidity. So let's say we have a container or a room with 50% relative humidity in the middle at a temperature of 20 degrees C. We'll assume the humidity inside the room is evenly distributed, meaning the vapor pressure would be the same throughout the whole volume. Now, if we measured the relative humidity instead at the corner of the room where the sun is shining and the temperature is 1 degree higher, then we would only read a relative humidity of 47%. The wrong interpretation would be to assume that the room was drier in that corner, but it is only the relative humidity that is lower. So relative humidity is also one of the most important quantities of humidity. It governs drying phenomena and impacts our sensation of humidity. It's also the primary physical variable that most hygrometers react to. There are many ways to quantify the water vapor concentration other than relative humidity. And so I'd like to give an overview of some of the more common units used in research and industrial process controls. We'll get into these in a little more detail, but I encourage you to access our free online humidity calculator. And this can help you see the relationship that exists between these different values. And if you change one variable, how it impacts the others. This link is probably not going to work here, but a web search will get you there as well. The dew point is a common parameter. It is represented by a temperature because it is the temperature at which the current amount of water vapor pressure will equal the saturation vapor pressure. And at this point, the rate of condensation would equal that of evaporation. It's witnessed as condensation on surfaces that are at or below the dew point of the air. You can think of this window here, or maybe the dew on the grass in the morning, or a cold glass in the summertime. While represented by a temperature, this unit is not temperature dependent. That is to say, changing the temperature is not going to change the dew point. The dew point represents the amount of water vapor by comparing it to the temperature of the corresponding saturation vapor pressure. The dew point is pressure dependent, however, and increasing the pressure will increase the dew point temperature. This unit is most used in meteorology and in dry compressed air. Now, absolute humidity is used to represent the amount of water vapor in a given volume. It's not temperature dependent, like dew point, and it is pressure dependent, again, like dew point. This is because the pressure is going to affect the volume calculation. This can be a useful unit in processes that have varying temperatures, like high temperature applications where a sensor needs to be installed in a different, cooler location. The mixing ratio is a gravimetric unit, which calculates the weight of water vapor related to the weight of the other gas components. This unit is independent of temperature and pressure, making it useful in many processes with varying temperature and pressure considerations, conditions. It better represents an absolute quantity of the moisture present. Now, most of you are familiar with parts per million. It's used most often in liquid measurements, but is also relevant in the fluid of air and gases. It can be characterized by volume or weight, with volume being the more common. This calculation is not linear, however, and depends on the comparison between the total gas components or the dry gas components. Like the mixing ratio, Vaisala instruments use the dry basis for our values. The wet basis would be to incorporate the weight of the water vapor also. This parameter is most often used in extremely dry applications where only a few ppm are being measured of water vapor. The wet bulb temperature represents the lowest temperature achievable through evaporation. Now, if you remember, the molecules with the most energy or temperature escape during evaporation, effectively leaving the cooler molecules behind. This lower temperature is then compared to the ambient temperature to calculate the relative humidity, as the current humidity level in the air will determine how fast evaporation can occur. This unit is used in psychrometric measurements and in enthalpy calculations, and it is a common measurement used in cooling tower applications. So this brings us to our next topic, the methods of measuring humidity. Throughout the history of relative humidity measurement, there have been numerous approaches to the task. The first attempt to measure humidity was made by Leonardo da Vinci in the 1400s. His gravimetric hygrometer was simply a balance with a bale of hygroscopic material, paper, or something similar on one end. And with increasing relative humidity, more water was absorbed by that bale, and the increased weight could then be measured. Other early hygrometers measured the physical change of materials that would absorb water vapor, and examples include animal hair, membranes, and paper coils. These methods proved to be inaccurate with limited measurement ranges and high maintenance requirements. Other methods of calculating relative humidity were then developed, and some are still used today, such as the sling psychrometer here on the right, and the chilled mirror hygrometer represented in the bottom left diagram. These methods use evaporation and condensation to measure and calculate the humidity levels indirectly. And while they work, they're not always ideal. And now, demand continued for more accurate and full range relative humidity measurements in weather and research applications, and a more accurate and low maintenance solution was needed. After the invention of the transistor, the first electrical humidity sensors were developed. These sensors were based on measuring the electrical resistance or impedance, as materials would absorb water vapor and their resistance characteristics would change accordingly. These sensors did work fairly well, but also had their drawbacks such as poor stability, limited accuracy, and difficulty responding quickly to decreasing humidity levels, which is also known as hysteresis. This table gives us a rough comparison of the technologies available in around 1970. They all have their advantages and drawbacks. The mechanicals are slow and delicate with too many inconsistencies and poor stability. Psychrometers get dirty and can drift. They need a lot of maintenance too, as you need to keep the wet bulb wet. Chilled mirrors have a high accuracy that makes them very desirable in reference instruments, but maintenance, portability, and cost considerations make them less ideal for most applications. So in this list, the resistance sensors look pretty good, if you can accept the hysteresis and the drift. However, there's still demand for a more robust humidity sensor that required less maintenance and responded faster in both directions. Higher accuracy was also in demand as small changes in humidity are observed to have very distinct results. A case in point is the radiosonde, or the weather balloon. The history of Vaisala is built on a radiosonde application, as Professor Vilho Vaisala, pictured here, founded the company in the 1940s after developing the first commercially viable radiosonde. A radiosonde measures the temperature, pressure, humidity, and the wind profile of the atmosphere, and then transmits the information to the ground for meteorological forecasts. They first used a hair hygrometer connected to a capacitor for the humidity measurement. Now, a radiosonde is a very challenging application for a humidity sensor. It has to be fast, it has to recover from getting wet, as they would frequently travel through clouds. It must be accurate and able to withstand a rough ride through the atmosphere. The hair hygrometer was not the ideal solution. It's very slow, fragile, and inaccurate. So to address these challenges and provide more reliability to weather observation technology, Vaisala developed the first thin film polymer capacitive humidity sensor in 1973. Known as the Humicap, the Vaisala humidity sensor was able to measure the entire relative humidity range. It could get wet and recover quickly with high stability and fast response times. This technology allowed weather balloons to respond to rapidly changing atmospheric conditions, which provided better insight into the world's weather and improved our capability to make meteorological forecasts. The composition of the Humicap sensor is a sandwich of sorts, built upon an aluminum base. We have a hygroscopic polymer material layered between two electrodes. The water vapor passes through a porous upper electrode and interacts with the polymer. The amount of water vapor in the air will change the capacitance of the polymer, which is then measured by the two electrodes. It responds directly to the change in relative humidity, releasing the water vapor immediately to maintain equilibrium. The upper electrode is only permeable to water molecules, resulting in extremely good chemical resistance, the ability to operate in dusty, dirty, and oily environments. This all means we have a compact, durable, sensitive, low drift sensor well suited for atmospheric conditions. Since then, Vaisala has adopted the Humicap into instruments for HVAC and a myriad of other industrial and life science applications. The thin film polymer capacitive sensor has become the industry standard and is imitated but never copied by most major humidity sensor manufacturers today. So speaking of accurate measurements, now let's take a closer look at what that actually means and how to maintain it. There are a number of different ways to express accuracy, and they go beyond the simple difference between the measured result and the true value. Repeatability is the ability to provide consistent results when the measurement is repeated under similar conditions. This is also known as precision. This is useful when the absolute accuracy is not as important, but the ability of the instrument to agree with itself is paramount. This plays an important role in quality control. Linearity is the ability to balance the measurement conditions with a consistent output. This is important with signal outputs and when challenging variables can affect the measurement. We'll look at an example a little more closely as in regards to how a sensor can perform consistently in elevated temperatures. Hysteresis, I mentioned in our context, is the response rate of a sensor that is going from dry to wet or wet to dry. Traditionally, humidity sensors respond faster to increasing humidity and slower to decreasing humidity as the sensor takes time to dry out. Stability refers to the drift in accuracy of the sensor over time. Most, if not all, sensors drift in that their measurement error increases over time. This is why we calibrate and adjust sensors, and poor stability leads to more cost and effort. And uncertainty. This refers to the quality of the measurement, the reference instruments, and their calibrations to accepted standards. This will dictate the overall quality of your calibration. Of course, it is ideal if these characteristics are known for the instruments you use. Unfortunately, not all manufacturers will go through the effort of testing and publishing these specifications. Often manufacturers outsource components and simply don't know the answers, and others cherry-pick conditions to make their products seem more capable than they are. As promised, here's an example of poor linearity at an elevated temperature of 70 degrees C, or 158 degrees Fahrenheit. The x-axis is the relative humidity, and the y-axis is the percentage of error. This manufacturer's specification only provides a narrow range for temperature, and the accuracy at 70 C is not provided. The shaded area is the only spec we have to go on, and as you can see, the readings suffer in accuracy for the entire range of the humidity. The nonlinearity is evident over the humidity range as the elevated temperature and the error increases consistently. The other side of that scale is a complete set of specifications that accurately describe the linearity and the temperature dependence of the sensor. You'll find the graph on the left or a similar one on all available Vaisala instruments, covering the entire designed measurement ranges for temperature and humidity. If your process or test conditions fall outside the more basic specifications, you should settle for nothing less than a complete spec. Now, every measurement you can take is imperfect in one way or another, and the most accurate instruments will have error if calibrated against a poor reference. This is because of the nature of measurement and because we can't ever really verify if a perfect measurement occurred. The next best thing is to quantify the possible inaccuracies into an uncertainty value. This uncertainty can be summarized as the range of possible values where the actual value could be. It is expressed by the root sum square of all the known inaccuracies from all the other instruments in the chain of calibration, as well as the accuracies of the instrument you're using. In order to do this, a chain of traceability must be established back to the international standards, and that allows us to prove our measurement. So, if the uncertainty in calibration is not known, the traceability chain is broken, and then the measurement is worthless. Traceability is our proof of the quality of our measurement. Without it, we could never know if the instrument was adjusted to a false reference, and then there could be no trust in the results. As you can see, the farther you deviate from the measurement standard, the higher degree of uncertainty is possible for the measurement. Knowing how far you are from that standard will allow you to make better decisions based on the information you receive from your measurements. And for those of you who don't recognize the picture in the top right, this is our new kilogram standard, or the new kilogram standard, which is based on light particles and Planck's constant. The previous was a platinum iridium cylinder. Standards for traceable calibrations have been established to protect measurement integrity, and the most common is the ISO 9001 standard. The National Institute for Standards and Testing, or NIST, is a familiar agency in the United States, and they adhere to this standard. They also use some Vaisala instruments for their own lab monitoring. They establish a baseline for record keeping and for validation. More strict traceability standards also exist. And the ISO 17025 standard is common in metrology. It establishes a more strict system for record keeping, and calibration data is recorded in a more thorough fashion. Calibration personnel are also required to maintain training records and demonstrate proficiency. These accredited calibration facilities are audited and approved by agencies on a regular basis to ensure both quality and the competence of the calibration labs and their organizations. So what does this mean for you? First, you need to know what type of measurement you're taking, why it matters. From there, you need to assess the best way to ensure that measurement is a quality one and how to maintain it. Quality management procedures will likely have guidelines to follow, but you can always return a quality instrument to the manufacturer for service, or you could find a third-party provider who can perform a traceable calibration and furnish a certificate with an uncertainty information. From there, you can establish a service interval based on either the manufacturer's recommendations or your desired accuracy and the stability specification of the instrument. But sometimes a traceable calibration isn't really needed, and often a simple spot check with a traceable reference or a handheld instrument will let you know that things are working as designed. So it's up to interpretation. Now I'd like to take a moment to go over some of the tips and pitfalls that we at Vaisala have come to see over the years of troubleshooting and helping customers make the best measurements possible. A common wall sensor for humidity and temperature are installed all over the world, but certain factors can make or break this measurement. One possible issue is the interwall space behind where sensors are mounted. Much like a leaky wall outlet, cold air can flow from inside the wall and into the sensor, causing false readings of both humidity and temperature. The wall itself could also be a heat sink or a heat source, given the materials, or the level of insulation present. This is more common on exterior walls, and the temperature error will affect the humidity reading also. For carbon dioxide measurements, fresh concrete walls and new construction can absorb CO2 for months, causing incorrect low readings in sensors that don't have their own internal reference measurement. These issues can all be remedied by sealing wire holes, insulating, or blocking behind the sensors, and taking care not to mount on surfaces that have potential temperature risks. For example, in a sunny corner of a room where the window is open. In duct installations, location is also key. Problems arise from mounting sensors where condensation can occur naturally, like in attic ducts in the humid south, to places where humidity is generated intentionally, like the image I have here. It may be easy to mount a humidity sensor near the humidifier, but we need at least 5 meters of distance between these two to ensure that the water droplets have sufficiently evaporated before they reach the sensor. And this is for 2 reasons. The obvious one is that the sensor can get wet and stop reading accurately. It won't read accurately until it dries out. The second is that if the sensor isn't getting wet, it's not measuring the water vapor from the condensed water droplets. Either way, a proper reading is impossible, and the system will use more energy to balance the desired space conditions. The other point of this image is to encourage the installation of a service port next to the duct sensors. This will allow for easier spot checking of the sensor to diagnose problems or to perform field calibrations if that sensor is capable. The last issue I'll highlight is another issue caused by temperature error. You can notice the theme here. Conductive cooling can have an effect on the thermal mass of many industrial-grade humidity sensors and processes. They are constructed of stainless steel for durability, but the mass of the probe can conduct heat into the process if the temperature difference is large enough between inside the process and outside the process. This can lead to significant errors in the measurement. These errors can be mitigated by mounting the entire measurement probe inside the process if your pressure levels allow, but the probe cables can be sealed with and not conduct much heat. Now, if the process is at a higher pressure and requires a threaded fitting, consider insulating the exposed section of the probe to the process piping. This will minimize the conductive cooling effect. Okay, so that is what I had for you today. I'd like to thank you all for your time and attention. Please visit Vaisala.com for more information, or reach out to our friends at Statesville Process here, who will be happy to help you with any of your Vaisala instrument needs. So now I'll take some time to answer any questions that you may have sent during the presentation. So let's see if we stop sharing here so I can see what we may have had here.
Are there any questions, guys?
No chat questions. If anyone wants to unmute and pick my brain, I'd be happy to. Happy to oblige. But we did go a little bit over the 30 minutes allowed, so maybe some people dropped out too.
You're good. Well, if there are no questions, guys, Justin, thank you very much. Very informative presentation.
Yeah, you're very welcome. Hope learned a little something.
Yeah,
Try to keep
absolutely.
things pretty general, give a nice broad overview of the topic.
Absolutely. And we've got a large crowd today, and thank you to everyone that showed up. We certainly appreciate it, and please join us in our future webinars as well. Thank you, guys. Everybody have a good day.
Very good.
Thanks.
Thank you.
Thanks,
Much
Justin.
appreciated.
Thank you.
You're welcome, everybody.
Thank you,
Take care.
Thank you, everybody.
Thank you very much.
Bye.